there is a very famous yet misunderstood quote by Galileo. If you want to understand nature, you need to understand the language in which nature is written. And this language is, of course, the language of mathematics. Now, without getting too much into the complexities of this sentence, it is basically true, especially in the field of kinematics, the study of moving objects, and in our context, the study of moving vehicles. Now, from my experience, this is a weak spot for computer science students, especially since we don't learn physics as a prerequisite in our syllabus. But since it's A, extremely important to understand the Kalman filter, and B, not so hard, we are going to cover it now. If you remember from your high school studies, there is a very simple equation that states S equals V times T. S, the displacement, V, the velocity, and T is a time. Let me give you a concrete example. Let's say that the velocity is 7 meters per second. What does it mean? That after 1 second, the vehicle has moved 7 meters. After 2 seconds, the vehicle has moved 14 meters. And after 10 seconds, the vehicle has moved 70 meters. Now, you can look at it differently unit-wise. V is measured in meter per second. T is measured in second. If you multiply meter per second by second, you get meters. Now, you could look at it differently from a derivative and an integral perspective. Let's say that we have a constant velocity v. Now, the constant velocity means that the vehicle doesn't change its velocity throughout the course. Since the velocity is a time derivative of the displacement, it means that the displacement is the integral of the velocity. And if I integrate v0, what I get is v0 times t plus c. C is the constant that we get when we integrate. But in the context of physics, we don't call it c, we call it x0. What does it mean, x0? Let's go back to our previous example. Let's say that I moved for 10 seconds. I should be at x equals 7t. You know, 7 times 10. But only if my initial position was at x equals 0. If, for example, I started at x equals 50, my final position will be 50 plus 70, 120. x0 will be the initial displacement where actually I started. And from this position, I add v0 times t, assuming that we are in a constant velocity model. Let's move on to a constant acceleration model, and let me give you a very historically important example. Let's assume that I go to the top of the Pisa Tower and I release an object. What will happen? If you remember, the Earth acceleration g is approximately 9.8 meters per second square. It means that if I release, don't throw, just release an object, after 1 second, its velocity will be 9.8 meters per second. After 2 seconds, its velocity will be 9.8 times 2 meters per second, which is 19.6 meters per second. And after 10 seconds, assuming that we neglect the air, its velocity will be 98 meters per second. This is a constant acceleration model, and this is a very famous concept in autonomous vehicle. Now, before we move on, there are other types of motion models, but we are not going to cover them in this course. Now, let's move on to the equations of the constant acceleration model. So let's start with the acceleration. So a as a function of t is constant, a0. What does it mean? That if I integrate the acceleration, I get the velocity. V as a function of t equals a0 times t plus c, the constant. In our example, it will be v0, the initial velocity of the system. And if I integrate again, I will get that x as a function of t equals v0 times t plus 1/2 the acceleration a times t squared plus x0. Now, in the context of the Kalman filter, we usually say that x as a function of t equals x as x at t minus 1 plus v0 times t plus 1/2 a t squared. It's very important to say that in the context of Kalman filter, what we usually do is to compute the motion equations from the previous state to the current state. The previous state means x at t minus 1, and the current state is x at t. So what we get is that the x as a function of t, let's say that we are in a constant velocity model, equals x at t minus 1 plus v at t minus 1 times delta t, the time displacement between the previous state and the current state. Below this video, you will find problems and exercises regarding the motion equations, constant velocity and constant acceleration. Please make sure that you are familiar with these equations before you move on. Why? Because understanding these equations is a mandatory condition for understanding Kalman filter. Good luck!